this is right.
Okay. Yep, okay, thanks for waiting. So now we're on to Stacey's talk.
Okay, so that was part one of my talk, and now on to part two. I'm going to be talking about some new results, which are joint work with Shantanu Chakraborty and Andras Gillian, who's right here. And so we have some new algorithms for the quantum version of the least squares problem, also called linear regression. And so the first thing I'm going to do in my talk is I want to actually state our results, which is non-trivial to do. And then if I have time, I would like to talk about some of the techniques we use, which is this block encoding that Robin's already mentioned. This is something that's sort of been developed in several past works, maybe more or less explicitly. And I think it's becoming clear that this is a nice framework for working with linear algebraic problems. Let me start by first defining the problem that we're going to talk about. So least squares fitting, or linear regression, is a problem that comes up. It's a very basic data analysis problem, or machine learning problem, if you like, where we're given some data points that are somewhat linear. So we kind of hypothesize that this data is arising from some linear function, but they're noisy data points, so they're not fitting perfectly on a line. And we want to give a model, a linear model, that describes this data so that we can, predict new data points, for example. So more precisely, we are given the data points as input in a matrix and a vector x and y, where the ith row of x and the ith entry of y encode the ith data point. So we have the ith row of x is giving us the independent variable, and then the ith entry of y is giving us the dependent variable. This is how we receive the data. And how we actually get this matrix and this vector is a very important question, which I'll talk about shortly. But for now, just assume that we're somehow given this data. And we make an assumption that the data is well approximated by a linear function. So specifically, we're supposing that there is some linear function f that describes the data, but then when we actually receive a data point, we get y sub I with some random error added to it. And so that's why, of course, this would be very easy if we just got some points on a line, but because of this noise, the problem becomes a bit more difficult. The problem of ordinary least squares is to find a linear function that well approximates this data in the following sense. So we want to find a vector beta, which is going to describe the linear function. And we want to find a beta that minimizes this expression here. So yi is our actual measured value f of xi, and this is our hypothesized value f of xi. It's hypothesized to be the output of this linear function, and we want to minimize the total squared error over all m of our data points. Yes?
Do you allow a constant term in your linear function?
Yeah, you can kind of just push the constant term into one of your variables. So we'll suppose no constant term, and that can kind of be taken care of by adding an extra dimension. Okay, so this is the problem of ordinary least squares. And with some manipulation, we can see that the beta that optimizes this will have this form. In particular, it's just the pseudo-inverse of x applied to y. Of course, if there were no error, then we would just be inverting a linear function. But here, in particular, there's some error. So this is the beta that we actually need to find. Okay, so another problem we might consider is a weighted least squares problem, where instead we're trying to minimize this weighted sum of squared errors. And this is good for cases where perhaps we know that some of our samples are better than others. And so we use some weights to sort of describe our confidence in the samples. And it's not part of our job to find these weights. We assume that they're given. And so if we assume they're sort of given as the diagonals of a matrix W, then we can see that, similar to the above expression, the optimal beta is exactly this, where we've just sort of had to scale things by W. And it can also be expressed in terms of a pseudo-inverse. And then the final case that we consider is generalized least squares. And this is for cases where you might know that your errors are correlated for certain points. The errors of certain data points might be correlated. And so we assume that in addition to the data points, you're given some invertible correlation matrix that sort of describes correlations between the errors. And then in that case, we want to find a beta that minimizes this expression. And here, this is the ijth entry of the inverse of omega rather than the inverse of the ijth entry of omega. And similar to the above, we have a closed form expression for this, so we want to find this beta. This is the beta that will minimize this expression, given in terms of the data matrix X and our correlation matrix omega.
Maybe you'll say this later, but is everything that you're going to say very specific to L2? Or because often people do L1 because of this outliers problem.
I see. No, yeah, everything here is specific to L2. So, I think for this problem, because it's called least squares, so I think it is normal to consider the squared error. But yeah, I think everything that I'm saying will not work for.
So the square has the property that it puts a lot of, if you have a few bad data points,
I see.
it's going to try to fit those because it's very expensive to not fit them because of the square. So sometimes you use L1.
I see. Okay. Yeah, it could be interesting to consider, but I think it would be much more difficult to sort of generalize these techniques. But it could be interesting. Okay. So these are some different varieties of this least squares problem, and we're not actually going to solve any of these problems in my talk. We're actually going to consider quantum versions of these problems. So whereas for the classical problems, we always wanted to find this vector beta, so we wanted to find a list of coefficients of the linear function, we're going to ask for something that's maybe less good, which is that we actually want to output a quantum state beta whose amplitudes are proportional to the coefficients of the vector beta. And of course, this is a less good thing to be able to do, but we'll be able to do this with much better complexity. And the hope is that since least squares comes up in so many different applications, maybe in some of them, it could be that it's good enough in some cases to get a quantum state beta. Although I have to admit, I don't know of such an application. I'm not going to talk about how this might actually be useful. I'll just talk about how we might be able to solve some of these problems, which I'll call quantum ordinary least squares, quantum weighted least squares, and quantum generalized least squares. Okay, so now I have sort of almost finished defining the problem, but I still haven't told you how the input is given, and there are a number of possibilities for this, and they change the problem, sometimes considerably. So let me talk about how we might actually access the input. One model that has been mentioned already in several talks is the sparse access input model. At least that's what I will call it in my talk. And here, so we want to somehow access a matrix A. We're going to assume that the matrix is sparse, so there's some parameter S that we know, and we know that all of the rows in A and all of the columns in A have at most S non-zero entries. And then we'll be able to query A in three different ways. So first we'll have some oracle that takes a row index I and a k between 1 and S, and it tells us the index of the kth non-zero entry of the ith row. And we'll have a similar oracle for columns, where for any column J, we can ask for the index of the lth non-zero entry in the jth column. And this helps us find non-zero entries of the matrix, which can be useful if there are only few of them. This could save us considerable work. And then we also have a third oracle, which for any I and j allows us to query the ijth entry of the matrix. Okay, so this is the sparse access input model. This is an input model, so we don't have to talk about how you would actually implement these oracles. They're just given to you. Now I want to talk about a different kind of input model where we access information that is stored in a certain way in memory. So we want our quantum algorithm to be able to access some classical information stored in memory. And one way for a quantum computer to access classical information in memory would be the model of quantum random access memory. So, so suppose we have some array of memory where we have, we'll call the contents of the ith memory cell x sub I. The classical random access memory model allows you to sort of, for any I, you can produce x sub I from this memory. Often this is counted as just sort of a constant time application, although in reality, this should take time proportional to log n, because we can sort of imagine that there's some tree-like structure hooked up to this memory, where if we want to query the ith index, the bits of I will tell us some path of length log n down this tree that takes us to the ith memory cell from where we can access x sub I. So we sort of can't really say that the gate complexity of this is log n, because this tree-like circuit is going to have n gates. But if you do a classical query, you're just going to go down a path of length log n, activating log n gates. OK, and what we want is a quantum version of this. So we want to be able to, even though this memory is holding some classical string, we want to be able to access it in superposition. So we want to be able to implement this map unitarily so that we can query a superposition of different indexes in the memory. Now, I'll just mention there's some debate about whether this is possible and what the cost of this should be. If you're sort of have a superposition of paths down this tree, then you can't really argue that you're only activating log n of the gates. I don't really want to get too much into this because I think I have not so much time, but we're going to assume that we have quantum random access memory that we can query in time log n. And if you really hate this assumption, well, the depth of the circuit is log n, so you can suppose that I have a parallel quantum computer. But we're going to assume quantum random access memory that we can query in time log n. OK, so given a quantum random access memory, now we want a way of encoding in this memory something like, say, a vector that's useful for our quantum computer. So one really useful thing would be if we can encode a vector that's a description of a quantum state and then efficiently generate that quantum state. So we want to define a data structure that can encode an n-dimensional vector so that in polylog n, we can generate a state where the amplitudes are proportional to the entries of that vector. There's also going to be some polylog 1 over epsilon due to truncating and implementing things precisely, but I'll kind of sweep all these details under the rug. OK, so how might we do this? So we're going to store V in a tree-like structure, where we will store the entries of V at the leaves of a binary tree. So for example, here's a 4-dimensional vector stored at the leaves of this tree. And at every internal node, we're going to store the L2 node of the 2 children. So for example, here we'll have the L2 norm of V0 and V1. Here we'll have the L2 norm of V2 and V3. And then at the root of this tree, we'll have the L2 norm of these 2 values, which is also the L2 norm of all of the leaves. So every internal node will have the L2 norm of its 2 children, which is also the L2 norm of all leaves below it. And I'll just show you for this example how we can, in log n operations, create this state. So first, we're going to, starting at the root, we're going to look at these 3 values, so the value at the root and the value at its 2 children, and that's going to tell us a rotation that we should do. So we're just going to do this rotation to generate this state. And then second, conditioned on the value in this register, we're either going to look at this child or this child and do the same kind of rotation using the node and its 2 children. So for example, if we're in the 0 branch of the superposition, we're going to look at this, at the value at this node and its 2 children, and we're going to do this rotation, which depends on these 3 values. And similarly, if we're in the 1 branch of the superposition from this node, we're going to do this rotation. And you can see that just in sort of operations proportional to the depth of the tree, we've already generated the state V. So this allows us to create this state given this data structure in log n operations. OK, so what can we say about this data structure? If we want to generate such a data structure, of course, if we're inserting n different values into it, it's going to take time proportional to n. That's something that we can't avoid. But if you imagine that you have some stream of values I, V, I, not necessarily in any particular order, you can insert each of them into this data structure in polylog time. And so you can sort of initialize this data structure from a stream of data in time that's like n polylog. However, once you already have the data structure, if you want to use it to generate this vector, that's just going to take polylog time. So we're going to, in our applications, we're often going to ask that we be given data in this nice form, which is a little bit cheating. But if you want to do some operation on a huge data set, you have to have collected it at some point. And if you had some forethought and stored it at collection time in this nice way, then you'll be able to use our algorithms.
I mean, if one can show that a classical algorithm with the same data structure can't solve the problem, then I think that's all the argument.
Sure. Yeah, I think it's like a worthwhile model with the information we have so far. Okay, So, but we actually want to encode not just vectors, but matrices as well. So we say you want to encode an n by n matrix. So here's one way that you could encode it. So I'm going to call this the Frobenius norm QRAM encoding of A. And you're going to, for every row of A, you're going to encode in the data structure I just described in this tree-like data structure. Every column of A, these are all just vectors. So you're also going to encode every column of A in this tree-like data structure. And similarly, you're going to encode a vector of the row norms of A and a vector of the column norms of A. And I'll call this the Frobenius norm QRAM encoding of A. It has some useful properties. So one, we can sort of initialize it from a stream of data in just some time proportional to the number of things, the number of non-zero entries in the matrix. We can also generate these sort of quantum states corresponding to the rows or the columns in polylog complexity. Also, less clear why this would be useful, but we can also generate this sort of vector of row norms or of column norms in polylog complexity. Okay. There's other ways we can encode A, and I'll mention the other ones that are of interest to us. So for any p between 0 and 1, I'm going to define mu sub p of A to be this quantity. So here we have the largest L2p norm of any row of A to the 2pth power, the largest L2 1 minus p norm of any column of A to this to 1 minus pth power. This is not such an important expression. I mean, it's important, but you shouldn't try to memorize it or something. And then for this value, I'm going to have a QRAM encoding called the mu p of A. QRAM encoding. It's going to also have some vectors related to A. I'm not going to say the details. The reason it's sort of named after this quantity is because this is going to be the normalization of some of the vectors in the encoding. Okay, and so I have these different ways of encoding matrix A in QRAM. They can all sort of be initialized in the same nice way. And then what you can do with them is going to be different, so your algorithms for working with them are going to be different as well. So now I've sort of at least mentioned all of the different input models that I want to consider, and I can start stating the results. So first I'll mention some previous work. So the first, this first algorithm for quantum ordinary least squares, which is by Nathan and Brown and Lloyd from 2012, is in the sparse access input model and has this complexity here where S is the sparsity, epsilon is the desired accuracy. Kappa is the condition number of the data matrix, and then M is the number of input samples. And this was improved in 2017 in the condition number. Of course, these could also, complexities could also be, these are both based on linear system solving, so probably by updating the linear system solvers that they use, the complexities could also be improved. So, these are not necessarily meant to reflect the state of the art, but these are as stated. And okay, then also recently, Karanitis and Prakash gave some algorithms for quantum weighted least squares in these different QRAM models. So here, mu should be thought of as ranging over the Frobenius norm or these mu sub p's that I mentioned. They're sort of a family of different input models. You have to kind of decide when you're storing the data which input model which way you're going to store it. And then given such an input, you get a quantum algorithm for weighted least squares, and the complexity is going to depend on the input model. So this mu would, for example, could be the Frobenius norm of this matrix, the weight matrix times your data matrix X.
Sorry, just a very naive question. If I wanted to do everything classically and get beta classically, what's the best classical algorithm for this?
For weighted least squares? Or
for getting beta, the values of beta.
For getting the values of beta? I mean, I guess that you would have to, there's a lower bound of n times m, of the dimensions of the matrix. I'm not sure if it's possible to meet that lower bound, but I think you can get pretty close. I don't know.
Okay, so if you do this and then you just use your beta to measure the coefficients of beta many times,
it's still better in some cases.
It's still better in some cases.
I guess in some cases. I mean, you also have this mu, right? So mu could be so mu, for example, if you're in the input model where this is the Frobenius norm, so that would be sort of the one that I showed most clearly, then this would be the Frobenius norm of A, and that could be like m,
Square
like square root of m.
In some cases it is better, even just going.
Even if you do, yeah. Okay, so our contribution is, well, our first contribution is that we improve this weighted least squares algorithm. So we improve from kappa to the 6th to just linear and kappa in also all of these different mu QRAM models. We also improve the dependence on epsilon from 1 over epsilon to polylog 1 over epsilon. And our algorithm also works in the sparse access input model. So with essentially the same algorithm in the sparse access input model, we now get complexity that depends on the sparsity. And these are for weighted least squares, and we also give the first algorithm for quantum generalized least squares. Now here, remember, the input is, we have x, and we also have omega in the input. And so this depends on the condition numbers of x and omega. And then these mu's depend on your input model. So for example, if we're in the Frobenius norm input model, this would be the Frobenius norm of x, and this would be the Frobenius norm of omega. And this algorithm also works in the sparse access input model, where now we have the dependence on the sparsity of x and the sparsity of omega. Yep.
Can I ask again? I think it's the same question, but just a question of lower bounds. So because of your, it wasn't clear to me, like because of your data structure, so in the classical case, is it clear that this n lower bound, that's a lower bound? I could imagine like that data structure allows me to sample from my data. So I could imagine subsampling and then solving the problem. And then that would allow me to sample from the coefficients of beta or to get some kind of a maybe decent N2 approximation.
Yeah, okay, so it's true, it's not completely clear that the naive lower bound still holds. Certainly there's nothing known that you could do with this data structure.
Because it hasn't been looked at, or?
It could be because it hasn't been looked at.
Yeah, that's what I would understand, work in sublinear time by doing.
Yeah, I mean, I sort of think that, like, yeah, okay, I would be surprised if it works in general, but there might be good heuristics or something that, yeah. Yeah, that's a good point, I guess. We would want to, like, compare what you can do classically with these data structures that are kind of, I mean, for a really fair comparison, I think you should even allow the data to be generated in the same amount of time, but to make a good classical algorithm as well. But I don't know of anything that then does better than n times m. Okay, so now that I've managed to state our results, I want to talk a little bit about the techniques that we use. And now I want to talk more about this block encoding framework that Robin mentioned. And so I'm going to define now another possible input model, which is that the way your quantum algorithm interacts with the input A, you want to solve some problem where at least part of the input is some matrix A, and the way you're going to interact with this matrix is that you have some unitary where A is the top left block. A is not necessarily unitary itself, and I'll try to justify why this is a good input model. You might be thinking, how do we implement this unitary? But I mean, this is just the input model, so we're making the assumption now that we have such a unitary. You might also notice that this is not generally going to be possible, because this will only be possible for A that has spectral norm at most 1. So we could also allow A to be scaled by some constant alpha. And of course, we'll also allow some error. So you can just approximate a matrix of this form. And then more precisely, we'll say that U is an alpha A epsilon block encoding of A if we can approximate this matrix of this form with alpha here using A auxiliary qubits. So we have the space that we need our matrix A to act on, and then we have little a auxiliary qubits. And so more precisely, if we kind of isolate the top left block of U by looking at the parts where the ancilla qubits are set to 0, then we'll have something that, if you scale it by alpha, gives A to within error epsilon. So notice that we're actually epsilon over alpha approximating. So our unitary is epsilon over alpha approximating a matrix of this form. Okay. So this is what we call a block encoding. And now, okay, what's something obvious that we could do with a block encoding? So one thing we could do is this problem, this very basic thing where we just want to multiply a state by a matrix, by a not necessarily unitary matrix. So we want to be able to take some state B and output some A times B up to normalization. And in all of our applications, we will always be assuming that B is something that you have some subroutine for generating. So we don't have to use the oblivious amplitude amplification, which we could not in this case. Okay, and we can pretty easily do that in the setting. So if you have some unitary of this form, you can apply it to B and all of the ancilla set to 0. And so that's going to be pretty close to just taking some unitary with this block in the top left corner, multiplying it with this vector in the top here. And so that's just going to give you A applied to B up to this scaling in the part of the state where the ancilla is set to 0, plus something that has the ancilla not set to 0. And so now using amplitude amplification, you can just amplify this part of the state to get the desired state. And the number of rounds you'll need will be linear in alpha, your scaling factor. Okay, so if you wanted to do matrix multiplication by this matrix A, then this would give you a way of doing it. So this is just a really basic thing that you could do with a block encoding. Okay, so now I'm going to talk about how we implement a block encoding because it's really nice to say if we had a unitary of this form it would be useful, but why should we ever assume we have a unitary of this form? Okay, so let's try to think about how to implement this. So suppose I have two unitaries, UR and UL, and I'm going to call the first n columns of UR psi1 up to psi n. So they're the first n rows of UR dagger. And you might act on a space of dimension much larger than n, but I'm only going to give names to its first n columns. And similarly, I'm going to call the first n columns of UL phi1 up to phi n. And then if I multiply UR dagger UL, I'm going to get something that in the top n by n top left block, I'll have this n by n matrix whose entries are given by psi I, phi j. Nothing I've said is deep or interesting so far. I'm just sort of telling you how matrix multiplication works. So this is, so far they're very simple. Now I want to define some particular psi i's that have to do with A. So now I'm going to let psi I just be a superposition whose amplitudes are the values in the ith row. So this is just a state corresponding to the ith row of A. And I'm going to define phi j is just going to be a superposition over the row norms of A. The j is just sort of going to affect a label here, but really it's all sort of the same superposition. And then you can see that if I define the vectors this way, I do have that psi I phi j is just the ijth entry of A up to the Frobenius norm. So what that means is that UR dagger UL is a block encoding of A. And so to implement a block encoding of A, it would be sufficient to implement UR and UL. So UR is just any unitary that maps I between 1 and n to this row superposition. And UL is just any unitary that maps J to this superposition. And these are superpositions that I can generate if I have my matrix A stored in the Frobenius norm QRAM encoding. And so this means that if I have A in this Frobenius norm QRAM encoding, I can implement this block encoding of A. And without going into the details, more generally, for any mu, that's the Frobenius norm or one of these mu sub p's of A, then if A is in the mu QRAM encoding model, there's some block encoding with scaling mu that I can implement with polylog complexity. And we also have that if A is given in the sparse access model, there's a way to implement from that a block encoding in complexity polylog n over epsilon, where now the scaling is in terms of the sparsity. So if I develop an algorithm in the block encoding framework, that algorithm will apply both to these different QRAM models and also to the sparse access model. Okay, so this is one reason why you might want to develop algorithms in this model. But another reason is that it is actually kind of nice to work with this model. So let me show you some of the things that you could do if you have your input in this model. So one is that if you have two block-encoded matrices, it's easy to compose them. So you can kind of multiply them, put the ancillas in the right place, and you'll get a block encoding of the product. So a block encoding of A, a block encoding of B. You can easily get the block encoding of the product of AB. This is quite straightforward. But there's more complicated things that we can do. So for example, Lo and Trong showed how to do Hamiltonian simulation in this model. So starting, I'll put this in sort of the words of our work, but starting from a block encoding of a Hamiltonian, H, you can produce a block encoding of e to the ith for any t. And this, implementing this v will require calling this u as a subroutine. So specifically, if the complexity of implementing this u is some t sub u, then you'll be able to implement v in complexity like this. So the algorithm for implementing v will call u some number of times. And you can think of this alpha as being sort of taking the place of the norm of h. Okay, and then seeing that you can do Hamiltonian simulation in this model, a natural thing, especially after Robin's talk, that you might think is, can we also do linear system solving? And so we can. So given a block encoding of A, we can also implement a block encoding of A inverse. Here the scaling is in terms of the condition number of A. And if the complexity of implementing this block encoding is TU, then you have this expression for the complexity of implementing this block encoding. And so now we can see, we could use this to solve the quantum linear system problem. So in this problem, you're given some matrix A and some quantum state B, and you want to output A inverse B. So how would we do that here? Well, we could apply V, which we know how to implement in this complexity, to B with some ancillary qubits set to 0, and we'll get this, which we can amplify to A inverse B. But notice that we'll have to amplify this, we'll have to run V like linear in k times. And so the complexity of doing this will be, in kappa times, the complexity of doing this will be kappa times this expression, which will in particular be quadratic in kappa. And in other models, we know how to do this in a way that is linear in kappa. And so in this model, we can also do quantum linear system solving in time that's linear in kappa, but we have to sort of leave the block encoding framework to do that. So we also show that given a block encoding, we can solve the linear system problem in time that is linear in kappa, and it's using the same techniques as have been used before, which is the variable time amplitude amplification. Okay, so now that I've shown you some of the things you can do with block encodings, I will very quickly talk about how you can solve the problems that I spent so long defining, in particular generalized least squares. And luckily, it's very simple to work in this framework, so I can do this very quickly. The problem, again, is that our input is some vector y. We'll assume it's in QRAM. And some matrices x and omega. I'll assume I have block encodings of them. That might be because I'm in the sparse access input model, or it might be because I'm in one of these QRAM input models. All of them lead to nice block encoding inputs. And I want to output a state proportional to this. And so since y is in QRAM, I can easily generate this state. And so if I had a block encoding of this whole matrix here, I would be done. I could just apply the block encoding to y. So I'm going to now build up a block encoding of this. So first, I'm going to use my block encoding of omega to generate a block encoding of omega inverse. And then I'm going to use my block encoding of omega inverse, and I also have a block encoding of x as part of the input. Now I can generate a block encoding of x transpose omega inverse. Next, I can use my block encoding of x transpose omega inverse and x to get this block encoding. Now I can use this block encoding to get a block encoding of its inverse. And now I can combine these two block encodings that I've built up to get a block encoding of the entire expression, which I can then simply apply to y and do amplitude amplification on this whole process. So this is like a very simple way that I can just sort of, using, here I only had to use these two techniques of being able to multiply block encodings and invert block encodings, and I could just build up this larger algorithm. Now in doing this, I could not get the benefit of the variable time amplitude amplification that gives me better dependence on the condition number. And so we can actually, this is sort of a really nice algorithm, but with a little bit more work, you can actually do better, but it's sort of less nice. Okay. A few things I didn't mention. So I won't talk about the details of variable time amplitude amplification, but it's some way that for certain algorithms you can speed up amplitude amplification. We also give a technique that allows you to get the same speed up for estimating the amplitude or estimating the success probability of a variable time algorithm. I think this is a useful technique, so you can ask me or Andres more about it later. And using this, we also get some algorithms for estimating electrical network quantities in the QREM model, in the various QREM models. Okay, so I'll just mention some further reading. So this is the result that I've been talking about, and you can also read more about block encodings and even some additional techniques in this paper, which is just went up on the archive last week. So thank you for your attention.
So can you comment on, when these kind of ideas can be actually useful? Can you envision kind of a problem? I guess I have my more specific question. So I guess some of these kind of ideas, in principle, can be related to machine learning, right?
Right.
So can they be useful for, I don't know, quantum machine learning or quantum phases or something like that? I mean, I'm just,
Yeah, so I guess that's a good question. I don't know the answer. For this to be useful, I guess you would have to somehow make use of having a quantum state that encodes your solution rather than actually getting the solution. And it isn't clear how useful that would be. So hopefully there would be some place where this would be useful. But So I guess the answer is I don't know. And you sort of asked first about if I could envision this being used soon. And I think maybe this is not necessarily going to be good for really near-term stuff. I haven't really thought about that. I think this is more of a large scale.
In principle, I guess in the physics domain, recognizing many body phases is actually a kind of problem where you can apply because if you have some kind of complicated quantum state, you will, for example, want to check if it's in the right phase of some complicated.
Yeah, I mean, maybe, I guess it's possible that you could use your output state to kind of do this, some sort of classification, but this is really speculative, so maybe you can say more.
For problems that you're taking a look at, standard or other standard quantum algorithms like quantum Boltzmann training or various forms of quantum neural networks would be a lot better suited in order to classify, say, what phase the ground state of a many-body system is in, for example. What this would do a better job of is a case where you're yielded a ground state or a state out by some process. And what you'd like to be able to do is like to be able to do a reconstruction of that state in terms of a linear combination of other quantum states that are yielded by other processes. So you can do forms of tomography with this that might be challenging to do with other methods. But whether that's practical in and of itself is still not clear. But it does enable something that's non-trivial at the very least.
Okay. Is there any more questions? Well, let's thank Stacey again, and we'll be